Now we transition into permeability. If porosity was storage capacity, permeability is the ease of flow. This is the property most strongly connected to well productivity. Permeability measures the ability of a porous medium to transmit fluids. It is a rock property describing the conductivity of the pore network. Explained clearly, permeability is not a property of the fluid, it is a property of the rock structure. Fluids matter through viscosity, but permeability describes the pore throat network itself. Also emphasize, permeability is an intensive property, meaning it does not scale with sample size. It reflects the microstructure of the rock. This slide introduces absolute permeability, single phase, 100% saturation of one fluid. Effective permeability, permeability to a specific phase at a given saturation in multiphase flow. Relative permeability, normalized effective permeability, used in reservoir simulation and recovery analysis. Takeaway message: in real reservoirs we almost always have multiphase flow, oil plus water, gas plus oil, etc. So relative permeability becomes essential later when we discuss water flooding and enhanced recovery. Permeability can be estimated from multiple data sources: core analysis, direct lab measurement, well tests, field scale transmissibility in kh.rft/formation tester, small scale in situ tests, production data and production logging, infer contributions and flow profiles, log data, including NMR-based estimates calibrated with core. Key message: permeability is highly variable. It is one of the hardest properties to predict, so engineers use multiple lines of evidence. This slide introduces Darcy's experiment. Steady-state flow through a porous medium is proportional to pressure head difference in area, and inversely proportional to length. Teach the meaning: if you increase pressure difference, flow increases; if you increase sample length, flow decreases; if you increase cross-sectional area, flow increases. Also teach assumptions: laminar flow, single phase, homogeneous sample. Darcy's law is the foundation of most reservoir flow modeling. Permeability has dimensions of length squared. In SI units it is m superscript 2, but in petroleum engineering we often use Darcy and milli-Darcy. Because most reservoir rocks have permeability far below 1 Darcy, so milli-Darcy is convenient. Also mention that oilfield unit systems often require conversion constants because they are non-coherent. This is why careful unit handling is critical in reservoir engineering. Here explain what 1 Darcy physically represents. The Darcy is defined from a reference flow condition in Darcy's law using standard parameters. If permeability is higher, the same pressure difference produces higher flow rate. If viscosity is higher, the same permeability produces lower flow rate. This is why heavy oils produce more slowly even in good rocks. This slide generalizes Darcy's law to include both pressure and gravity effects. Teach the practical meaning: in dipping reservoirs, gravity can contribute to flow. Fluids of different density behave differently under gravity. That's why structural dip and density differences influence contacts and flow. Reservoir engineers often combine these terms into a single potential so that Darcy's law becomes easier to apply in non-horizontal systems. This slide signals that permeability measurement depends on flow rate, pressure drop, geometry, and fluid viscosity. Also, borehole measurements like caliper logs matter indirectly because borehole condition affects some log responses, and production performance can be affected by near wellbore effects. In this section we now move to lab measurement methods. Here emphasize that the most controlled direct measurement is the core holder method in the lab. We push a fluid through a core sample at known rates, measure inlet and outlet pressure, and solve Darcy's law for permeability. Explain each variable: flow rate, viscosity, area, pressure drop, and length. Teaching message: permeability is not read directly, it is inferred from a flow experiment. This slide is mainly a visual header, so use it to frame the topic. In the lab we can measure permeability using whole core method, core plug method, sometimes specialized tests for fractures or anisotropy. Then remind students, lab permeability often represents matrix permeability, and may miss fracture contributions if samples are too small. Whole core method uses large pieces from the original core, with diameters typically 2.5 to 5.5 inches and lengths from inches to feet. Explain why it matters. It is better for heterogeneous formations because it samples larger scale variation. The disadvantage is cost and practicality. You cannot test too many whole cores. Engineering lesson: choose the measurement scale that matches the heterogeneity scale. This slide reminds that different lithologies require careful plug selection. For heterogeneous rocks, whole core may be needed. Teach the student habit: never trust a permeability value without asking, was the sample representative? Was it damaged? Was it cleaned properly? Was confining pressure applied? Whole core tells you the truth at a larger scale. These cores preserve heterogeneity, bedding, fractures, and laminations that plugs may miss. The standard workflow begins by preparing the sample, either by cutting core plugs from the whole core or by using a whole core specimen directly. The core is then cleaned to remove in situ reservoir fluids and dried carefully. Next, a test fluid is passed through the sample at a range of flow rates, while the pressure difference between the inlet and outlet is measured for each condition. Testing at multiple flow rates is essential because it confirms whether the flow follows laminar behavior and also helps reveal any non-Darcy or turbulent effects that may influence the measurement. As a quality control step, we plot flow rate per area versus pressure drop per length. Under laminar flow conditions, the data should form a straight line through the origin, consistent with Darcy's law. The slope of this line reflects the relationship between permeability and fluid viscosity. However, if the data curve away from linearity at higher flow rates, this suggests the presence of turbulence or other non-Darcy effects. Therefore, permeability measurement should be understood not as a single fluid injection test, but as a control procedure that also verifies whether the correct flow regime has been maintained. Liquid flow is commonly used for permeability measurement because liquids are nearly incompressible and generally provide more stable, straightforward data under Darcy flow conditions. They also avoid certain gas-specific effects, such as expansion and slippage, that can complicate interpretation. However, liquid testing may introduce fluid or rock interaction problems, including mineral reaction, clay swelling, or wettability alteration. Gas can also be used, and in tight rocks gas permeability testing is especially common because gas can move more readily through very small pore systems. In such cases, the measured gas permeability must be corrected for gas slippage, known as the Klinkenberg effect, since the apparent permeability may be higher than the true intrinsic permeability. This slide highlights an important practical reality. Laboratory permeability is highly sensitive to testing procedures and sample condition. Errors can arise from core handling, cleaning methods, and sampling strategy. Additional uncertainty may come from fluid-rock interactions, especially when the testing fluid alters the pore system or mineral surface properties. Laboratory measurements may also differ from in situ behavior because the sample experiences pressure release and loss of confining stress. Furthermore, heterogeneity and fractures within the rock can make the measured value unrepresentative of the larger formation. In gas tests, apparent permeability may also be inflated by gas velocity effects such as the Klinkenberg effect. Students should understand that permeability is one of the easiest reservoir properties to measure wrongly when procedures are not carefully controlled. Core handling, cleaning, drying, storage, and sampling all affect permeability measurements. Mechanical damage during handling may create microcracks or plugging. Cleaning can remove fines, mobilize clays, and alter wettability. Drying may damage clay structure and lead to shrinkage or later swelling. Improper storage, including freezing or pore sealing, can create fractures or change fluid conditions. Finally, non-representative sampling can bias the result away from the true reservoir average. Therefore, permeability measurement must always be interpreted in light of sample integrity. Fresh water may interact strongly with clay-bearing rocks, causing clay swelling and a reduction in permeability. Flow experiments can also mobilize fine particles, which may migrate and plug pore throats. For this reason, the selection of test fluid is critical in laboratory permeability measurements. To minimize formation damage, laboratories often use brines or oils formulated to preserve rock integrity and reduce clay-related effects. Students should understand that rock is reactive, and the injected fluid can alter the rock microstructure during the measurement process itself. When a core sample is brought from the reservoir to the surface, it experiences a large reduction in confining pressure. This stress release can change the rock physically by creating microfractures or by altering the original pore structure. As a result, the permeability measured at the surface may not represent the true permeability under reservoir conditions. For this reason, laboratory permeability tests often apply confining pressure to the sample so that the test better simulates the in situ stress state of the reservoir. This helps produce a more realistic estimate of how fluids actually flow underground. An important concept here is stress sensitivity. In many rocks, especially tight reservoirs, permeability decreases as effective stress increases. That means permeability measured under reservoir stress can be significantly lower than permeability measured at surface pressure. If this effect is ignored, the laboratory result may overestimate the flow capacity of the formation. In naturally fractured reservoirs, laboratory core plugs often measure only the permeability of the rock matrix, not the full flow capacity of the reservoir. This is because a small plug may miss the connected fracture network that controls fluid movement at the field scale. As a result, the measured core permeability can be much lower than the effective permeability of the actual reservoir, where fractures provide fast flow pathways. This is why permeability must always be considered with respect to scale. A plug scale measurement may be accurate for the small sample, but it may not represent the behavior of the larger fractured system. In other words, permeability measured in the laboratory is not always the same as permeability controlling production or injection performance in the field. Geology also matters strongly. Some rocks contain minerals such as salt, gypsum, or other soluble components that may dissolve, precipitate, or change during handling, cleaning, or testing. If those minerals are altered, the pore structure may also change, which directly affects the measured permeability. This means the laboratory value may partly reflect sample alteration rather than original reservoir properties. This core report shows us that reservoir quality is not determined by one number alone. We must read porosity, permeability, anisotropy, and lithology together. In this interval, the rock has low porosity and extremely low permeability, which tells us it is a tight carbonate anhydrite system. Some pore space exists, but flow capacity is poor. This also reminds us that porosity does not automatically mean good permeability, and that permeability can vary with direction because of rock fabric.